To push 5G technology boundaries, we have been investing in building advanced prototypes of upcoming 5G deployments and designs. This demonstration utilizes our end-to-end 5G and our standalone test network in San Diego, operating in the 3.5 GHz spectrum with 100 MHz bandwidth. The multi-cell system supports G-Node Bs with advanced multi-user massive MIMO, along with the 5G next-gen core and 5G NR mobile test devices based on the Qualcomm Snapdragon 5G modem RF system. Last year, we showcased a system simulation of a sub-band full duplex system which provides the ability for a G-Node B to transmit and receive at same time in the same spectrum band. Since then, we have upgraded our OTA test network to get a step closer to full duplex operation in TDD spectrum. This year, our network can support sub-band half duplex, which enables dynamic TDD operation and allows for more flexible service multiplexing as well as improved latency and coverage. Here is our OTA network. We see two G-Node Bs and two devices. Device 1 on the left is driving uplink heavy bursty traffic sitting on the cell edge of G-Node B1, while device 2 on the right is driving downlink heavy bursty traffic served by G-Node B2. In the baseline scenario, we have a time division duplex system that is typically deployed with a fixed half duplex slot structure across the network. TD operation requires all cells to operate with the uplink downlink pattern to prevent crosslink interference. For example, we're using a slot structure that has 3 consecutive downlink slots followed by an uplink slot. Device 1 is utilizing a small portion of 100 MHz bandwidth due to power limitation being on the cell edge. Its performance is further limited by the 25% uplink duty cycle. In the case of sub-band half duplex, we dedicated a portion of the bandwidth for downlink and another for uplink. This allows the cells to use different slot structures to adapt to traffic needs and reduces switching latency. G-Node B1 adopts the DU-DU slot structure, delivering more uplink opportunities, whereas G-Node B2 maintains the DD-DU format to serve its downlink heavy user. In slot 1 and 3, both G-Node Bs are transmitting on downlink with no crosslink interference. This is also true in slot 4 for uplink. In the second slot, G-Node B1 is receiving an uplink while G-Node B2 is transmitting on downlink. The downlink to uplink interference is mitigated through subband operation, where uplink and downlink transmissions use different subbands of the channel, minimizing the leakage of downlink subband transmission to adjacent uplink subband reception. Device 1 uplink packet latency and perceived throughput are significantly improved due to increased uplink duty cycle, while device 2 still gets 75% duty cycle from G-Node B2. Downlink user perceived throughput and latency are mostly not impacted. Subband half duplex enables flexible deployments that can adapt to varying traffic requirements, allowing more efficient service multiplexing. We'll continue to make great strides towards subband full duplex, so stay tuned.
To expand 5G to new devices, services, and deployments, we have been working on pioneering future 5G technologies in 3GPP Release 16 and beyond. This year, we're showcasing how 5G is evolving into supporting new capabilities beyond data communications. This demonstration provides an overview of our work in the different front of 5G positioning. Earlier this year at MWC Shanghai, we showcased our collaboration with ZTE to prototype 5G single-cell positioning based on round-trip time and angle of arrival. The round-trip time measurement provides an estimate of the device distance from the G-Node B, and the angle of arrival derives the elevation and azimuth direction of the device. Combining both, the 5G system can determine the location of the device. The OTA network operates in China Mobile's 2.6 GHz band over 100 MHz channel. The G-Node B is mounted on top of a 6-story building with ZTE's massive MIMO base station with 64 TX-RX antennas. The location server is designed and operated by Qualcomm Technologies, and the device is based on Snapdragon modem RF system. From the walk test, we see the simple setup delivering 80 percentile horizontal and vertical accuracy of 2.1 meters and 1.2 meters respectively. It's important to note that this is the raw accuracy using only the 5G system for positioning, without the aids of temporal processing, GNSS, or other sensor data. Adding these elements can further improve accuracy. Since then, we have expanded this OTA prototype to support a multi-cell implementation with 5G NoBs. From this expanded effort, we have also tested 5G positioning capability for non-line of sight and indoor scenarios. From these results, we have shown that this implementation can provide robust location positioning service in most practical deployment scenarios. Moreover, we have also prototyped 5G positioning in our own end-to-end 5G wide area test network in San Diego. In addition to 5G NR positioning based on Release 16, we have also adopted machine learning techniques and sensor fusion to further enhance positioning performance and efficiency. These field testing results demonstrated that high-precision 5G positioning could play an important role to complement GNSS. Furthermore, Qualcomm's wireless AI technology is shown to be synergetic to 5G positioning. We're taking large strides towards realizing 5G positioning in the real world, and we continue to work with industry leaders in demonstrating 5G capabilities. You can find the 3 demos I mentioned here, and please stay tuned for future updates.